So far, we have looked at indefinite integrals. So we looked at something like this, the integral of f prime of x, and that has always, up to this point, meant an operation to find f of x, the antiderivative of f prime. And of course we have these plus c, gives us a whole host, and other problems we solved for the c. But that was an indefinite integral. Now a definite integral, which means we have bounds, let's say from a to b, of f prime of x dx, does not return a function, but rather returns a value. And in chapter 5, it's all about this integral representing something else than a parent function, but representing a way to get a value. In fact, we're going to think of the definite integral, again with bounds, as an infinite sum or a Riemann sum. And that is what chapter 5 is all about. Now, if we look at this curve here, I'm going to mark the left endpoint at A and the right endpoint at B. So that's where the function's x values start and stop respectively, so like this. You may have at some point related the integral to the area under the curve. So if I look at this as two different areas, let's say this is A1 up to this point here, and then this is A2, one might say that the integral equals A1 plus A2, but that only works in this case, and the point of this particular lesson is to make the area integral connection. Let's mark off some important parts of this second graph. So this is A, the, again, left endpoint, and this is B, the right endpoint. Each one of these partitions, notice they're not necessarily the same change in x, but each one, so we would call this first one change in x, boy is that small, of the first interval. And purple shows change in x of the third interval. Now each of these intervals, we can look at where the top of the graph is, or where this rectangle intersects the graph. And if I drop that down to the x, we're going to give these labels. I'm going to call this C3. That's the x value where the corresponding height of the third rectangle occurs. You might see that in the second one, it's similar in location, meaning a little bit farther to the left of the partition, and this here, x value would be labeled C2. The first one looks like the left endpoint of the rectangle, or very close to it, represents the C1. And then that pattern can continue. If I pick one out here to be the generic one, so I'll drop that here. Let's call this not the first, second, or third, but let's call this the kth interval. So this would be marked C sub k for the kth interval, and of course this change in x would be change in x of the kth interval. And then given that this is the function f of x, the height of the rectangle for this generic one would be f of c sub k. Likewise, f of c sub 3 would be the height of the third rectangle. I went ahead and labeled the change in x in this burgundy color here the change in x of the nth rectangle. So we have the first rectangle, the second, the third, we have some generic kth, and then we have some generic nth, or the last one would be the nth. Now what is the purpose of these rectangles? If I were approximating the area bounded between the graph of f and the x-axis, I could use these rectangles to come up with an approximation. I could say that the area is approximately the sum of the rectangles, where each rectangle is base times height, the height being f of c sub k, and the width would be change in x of the kth interval. And we're going to do that from k equals 1 from the first to the nth. And the area is approximately the sum of the areas of these rectangles. And of course that's going to occur on this interval from A to B. Now let's compare that to the actual area. The actual area would then get an equal sign, and you might be able to see here that if I took an infinite many of rectangles and added those up, that would give me the actual area. So I can write this statement as the limit as n goes to infinity, so I'm creating an infinite many of rectangles. Again, the sum from k equals 1 to n of f of c sub k times change in x. This is the idea of a Riemann sum, an infinite sum. And if I take that infinite sum, that will give me, behold, the definite integral of f of x dx from x equals a to x equals b, where of course this infinite sum occurred on the interval a to b. It is in this particular case that the definite integral equals the area bounded by the function f and the x-axis. So it is this case, but not all cases, that the area equals integral. In the second example, you will see how that slightly differs. Let's call this graph g of x. Notice that g of x starts above the x-axis and then it drops below the x-axis. Starting point at x equals a, ending point at x equals b. If, like in the first example, if I were to sum up g of c sub k, the height or value of the function g at c sub k, times the change in x of the kth interval, and I started with k equals 1 to n, what would that approximate? What would it approximate? It would not approximate the total area under the curve between f of x and the x-axis. It would not approximate that. So what would it approximate? If I think of the area above the x-axis as a1 and think of the area below the x-axis as a2, then this sum that we have below would be an approximation for a1 minus a2 over a to b, of course. You see, these values of g of c sub k, under some circumstances, it's not the height of a rectangle, but actually a negative value because g is below the axis. So I'm adding up some negative quantities together with some positive quantities. So you might even call this like the net area is one way to approach it. And if I were trying to find the actual value of a1 minus a2, then that would be the limit as n goes to infinity of the sum from 1 to n of g is c sub k times change in x sub k. Again, the infinite sum, also thought of as a Riemann sum, and that would give me the integral from a to b of f of x dx. I think you can see here then that the area is related to the integral, but the integral itself does not give us the total area bounded by the function and the x-axis. In this case, it gives us what we called maybe the net area. An integral is permitted to have a negative value. In fact, by how I can view this graph, there is more stuff below the x-axis than above, so the integral or net area would certainly be negative. And one last comment about this infinite sum. The f of c sub k's turned into the f of x's. There are an infinite many of those. And then another interesting part about this is that change in x, when that becomes so small, we think of it as infinitely small, and that's why that turned into dx. So we're summing up infinite f of x times dx over the interval x equals a to x equals b.